Welcome to the webinar on how 3D printing helps manufacturers ramp up production. My name is Alexander Kreis. I'm a content engineer here at Markforged, and I'm joined by Marco Medecki, our email marketing specialist, who will be helping with logistics and questions at the end. So the goal of this webinar is to help you understand where 3D printing fits in with regards to preparing a manufacturing line for production. So we're going to look at three key points here: how 3D printers can make parts strong enough for the manufacturing line, why manufacturing ramp-up is the pain point of product development, and how 3D printing can help resolve those pain points in manufacturing to streamline the ramp-up process. So first, we're going to go into why 3D printing can be used for manufacturing. A lot of the materials and tools used in manufacturing need to be very tough. Manufacturing tools experience repeated impacts, high temperatures, and lots of wear. Since 3D printing has been around for decades, many people have out-of-date impressions that 3D printing is either a cheap way to make fragile parts or a prohibitively expensive technology reserved for the highest value components. Markforged is upending those perceptions by selling affordable 3D printers capable of producing parts tough enough for manufacturing environments. Markforged has both metal and composite 3D printers, both capable of producing high-strength parts affordably and quickly. So what do we mean when we say strong? Markforged metal printers print parts with strength comparable to that of their base material, 17.4 pH stainless steel, as you can see on the right. On the left here, our composite printers are the only 3D printers on the market that embed continuous reinforcing fibers during the printing process to make parts that are 23 times stronger than ABS. This is just as strong as 6061 aluminum. Let's take a closer look at how this works. So here's an example of a customer of ours. They use composite 3D printed parts as end-of-arm tooling in their manufacturing automation cells. These gripper jaws experience repeated high-impact loads as they close around thousands of parts a day. So here's the model of the part, and we're going to take a cross-section of this part and show you what our printers can do to this part internally. So here's the cutaway view of the part as shown in our slicing software to describe how our printing process works. There are two materials at play here contributing to the success of the part. The white lines forming the shell and matrix of the part are a nylon chopped carbon fiber blend we call onyx. This material is non-marring and chemically resistant to coolants and machining fluids found in manufacturing. The yellow lines encircling the perimeter of this part represent the embedded continuous reinforcing fiber. In this case, it's Kevlar. So here we have that same cross section but with the real part now, so you can see what that Kevlar looks like in reality. The Kevlar is a continuous strand woven around the perimeter of the part. You can customize these reinforcing fibers and how they're laid out within your part to suit your strength needs depending upon your application. So here we've chosen to reinforce the shell of the gripper jaw because the load from the grippers gets applied here on the gripping face of the jaw. The Kevlar fibers on every layer absorb this load by distributing the load across the continuous strands, so the continuous strands are the key players in the part strength. With different fibers and different reinforcement patterns to select from, you can optimize your printed part for its loading condition. So with these high-strength 3D printing technologies put to work, our customer base has become worldwide, with local service and support from our network of value-added resellers. Our products are trusted by industry leaders in many verticals, ranging from manufacturing and automotive to consumer electronics. Our printers help these companies bring their products to market faster and cheaper by accelerating their manufacturing development process. So now that we've explained why 3D printing can print parts strong enough for demanding manufacturing environments, let's dive into the pain points of product development. Hardware development starts with a concept. You've identified a need and envisioned a solution. You then take that concept and prove it out with a physical prototype. Once your prototype looks and acts like you expect, the next step is tooling development. This is where you need to take your single model and figure out what is needed to make hundreds to thousands of it. You need to design your tooling and process to successfully produce your first production unit, and then launch production where you can focus on product and line optimization to increase yield and make more money. So the real pain point of product development is tooling. Ramping up the tooling for your manufacturing line is laden with unexpected costs and delays, is usually 200 to 300% over budget, and can be 6 to 18 months behind schedule. As a result, tooling becomes the most arduous and least efficient aspect of moving your product from your prototype to your production run, and no hardware product is immune to it. Let's dive deeper into why that is. So here's an ideal workflow for production line development. Numbers and steps can vary quite a bit depending upon the industry, materials used, and the size or complexity of the product that you're making, but these examples should give you an order of magnitude sense for how cost and time distributes in tooling development. First, you make your forming tools: injection molding, die casting, stamping, things like that, often forming the largest parts in the product like the casings or the housings. These are often the most complex parts of the product. Tooling for this step is usually expensive and time-consuming. Parts need to be machined and finished, often by a third-party service, and molds are made out of incredibly tough materials like tool steel so that they can endure the stress and heat of thousands of mold cycles. The next aspect of tooling development is machine work holding. In some cases, especially with forming processes like die casting, parts need to be post-machined for precision. In other cases, you may have other custom components to your product that just get machined from the start. These parts all need work holding with a few key requirements. The work holding needs to securely hold the part through many machining cycles without degrading, and the work holding needs to be non-marring so that it doesn't scratch the product. Our next step is joining. When I say joining, I'm talking about things like traditional metal welding, as well as processes like sonic welding or gluing. Fixtures are often necessary to align multiple components for whatever joining process you use, and need to hold those parts precisely and securely during the process. So some fixtures, like this bicycle welding fixture, can be modular to account for multiple sizes and styles of frame, while others may need to be highly customized and precise to allow for perfect alignment of components. So next we get to inspection. Whether you're running products or parts through a test rig for strength validation, or simply measuring a part with a CMM machine to make sure it meets specification, these steps need rigs or fixtures as well. And now for our last step in the line, assembly. All the parts are made, verified, and now need to get put together. Not everything needs an assembly fixture, but if you want your production line to be efficient, developing custom tools to help assemble your product makes your workers' lives easier and means more products in less time. This means your line has a higher yield and your products are less prone to assembly issues. So you may think at this point that you're done. These are the major process steps in manufacturing, and once the tooling for each step is done, you can move on to the next one and get your line running. However, the big time and money sink, and where the big struggle lies in production line development, is all in the iteration. Each of these tools needs improvement and fine-tuning to get working right. These iterations are why product launches get months to years of delay and usually end up 200 to 300% over budget. Each tool in your production line needs iteration to be successful. For example, a flaw in the injection mold design could cause flow issues with how the plastic fills the mold. This means the parts it produces are out of spec. Another example, the first revision of an assembly fixture could create a flaw in how some of the products are being assembled. This drops the yield of the assembly line and means that until that issue is fixed, your production line will not be running at full speed. Sometimes there can be severe issues downstream that require a slight product redesign. For example, a supplier for a critical component of your product could discontinue or update that component. This causes changes to your product and may force you to reevaluate your product's design. And before you know it, you could be sent back to square one. You'll need to find a compatible substitute, verify that it meets specification, and redesign your product to make it work. The whole process change equates to thousands of dollars and months of work that you may need to do all over again. And there are a bunch of other reasons to get pulled back to square one as well. Supplier changes, alternate subassemblies for product differentiation, or a change in the process that's made after production ramps up. These all create edits to the product that have the potential to restart the process over and over again. All of these improvements could be critical to your product or could improve its success substantially. However, all of these come at a cost. You need to run through another iteration of tooling design. In some cases, you may not need to go all the way back to the beginning because you never know what unexpected roadblocks could come up and where. But that does not mean that you are free from the cost of another iteration. So where does 3D printing fit into all of this? We know that high-strength 3D printers with continuous strands of composite fibers can create tooling and fixturing capable of handling manufacturing applications. So now we're going to go into how we can take this timeline and cost estimation and turn it into this. 80 to 90% drop in costs and going from a multi-year manufacturing line development process to getting your line up and running in months. We're not removing the iteration steps, as those are still critical to the success of your line. We're just making them more affordable and more efficient. Let's look at some examples. So back to the first step of forming. I'm going to talk briefly about a customer example for this one. One of our customers, Humanetics, makes crash test dummies for safety testing. One of the parts they need to make for these dummies is the silicone neck ring. They used to have to get these molds machined, and due to the complex geometry of the neck ring, they were extremely expensive, costing near $20,000 to produce. They can now print continuous fiber reinforced molds for this application for only $130. So the printing process makes these molds extremely affordable, and they can have these molds ready to go in days. Just for this one part alone, they have reduced the mold cost by 99%. So the cost and time of the forming tool process drops substantially with this application. Next, we have soft jaws for the machining process in manufacturing. Here we have another example, and you can see the jaws holding this part are 3D printed. These are reinforced with Kevlar so the clamping load distributes around the fibers and holds the part securely. These jaws are non-marring and tough, so they don't scratch the parts, and are conformal, so the jaws match the curvature of the part that's being machined, making it a very snug fit and very tough and able to endure many machining cycles. Normally, conformal jaws are a compromise because they entail higher feature complexity when machining the jaw itself. This increases the cost of the jaw substantially, but here we can save about 95% on cost, and again, these can be printed overnight. So we can cut the machining work holding iteration process down by that much as well. So next is joining. The high heat deflection temperatures of our composite parts make them suitable for MIG and TIG welding, and precision alignment features can be designed into these fixtures to help with component alignment before the process. This can be done for gluing and sonic welding as well. Overall, you can use custom joining fixtures to reduce setup time of the joining process and ensure precise alignment with custom features to help line up your parts. So these costs drop as well. Even if you're using the 3D printed components for just the first and second iterations of your fixtures and machining the final version as you refine the process, you're still already saving thousands of dollars and weeks of time integrating 3D printers into your manufacturing ramp-up workflow. So next is inspection. Traditional inspection fixtures are usually very generic and can do a lot of different things, but have a high associated setup time. With our printers, you can design standalone inspection fixtures that eliminate this setup time and precisely locate the parts to obtain accurate measurements for inspection. And we talked a bit earlier about how this relates to testing rigs if your products need to undergo testing for quality verification. Our printers can help here too, providing high-strength parts for testing rigs next day. So again, this drops the time and cost. Our last stop is assembly, and we'll share another customer example here. One of our customers, Dixon Valve and Coupling, uses our products to simplify ramp-up of manufacturing lines for new products by 3D printing the end-of-arm tooling for their automation lines. They create these pipe couplings that have a gasket pressed into the top of them, as you can see here. Dixon Valve uses these metal printed end effectors to pick up, place, and put down the threaded couplings in their manufacturing cell. They can get these jaws turned around in days instead of waiting weeks for their parts to return from the shop, and in addition, the 3D printed metal grippers are lighter than traditionally machined jaws. This means that they can both ramp up their line faster and run their line faster, producing higher yield and getting the line up to speed in less time. For each project in which Dixon Valve incorporates high-strength 3D printing, they save roughly $35,000 because they cut down on all of the iteration cycles and associated costs across their entire line. So their costs can drop from thousands to hundreds, and their iteration cycle drops from weeks to days. This means they can get new products out to market faster and for far cheaper than they did before when using traditional methods. So in general, comparing the traditional manufacturing ramp-up of long lead times and high costs to using 3D printing for making your tooling and work holding, you can introduce substantial savings to your product line. Engineers spend half their time waiting for parts to come in. With Markforged, you can print them out and install them on your line next day. So 3D printing with continuous strand composites or metals can provide an avenue for affordable, same or next day strong parts. By 3D printing your tooling and your fixturing on your manufacturing line, you can cut costs by 80 to 90% and decrease your production line ramp-up time by 75%.